and so the idea of there being a planet was found to be erroneous. The third component of the system is a stark contrast to the first two. It is a red dwarf with a mass approximately 12% that of the Sun. Its size is about 7 times smaller than that of the Sun. Its surface temperature is only slightly higher than 3000 Kelvin, and its luminosity is just a measly 0.17% that of the Sun. Of all the components of the Alpha Centauri system, it is this dim space object that is the closest one to the Sun, lying 4.25 light-years away from it. This is what earned it its name, Proxima Centauri, which is Latin for closest. Besides, the object is getting nearer and nearer. Thus, in 26,700 years, it will be only a bit more than 3 light-years away. Still, this star cannot be seen from the Earth on account of its low luminosity. Proxima is noticeably far from its two companions in the stellar system. This distance is currently around 13,000 astronomical units or 0.21 light-years, but in the next 300,000 years it is expected to gradually shrink to just 4,100 astronomical units. It takes Proxima 547,000 years to orbit around the system's common mass center. Unlike its two larger neighbors, the Proxima Centauri system boasts 2 confirmed exoplanets, as well as at least 1 hypothetical object. Besides, studies of the star in the infrared allowed scientists to assume that there is a dust ring and probably a great number of small celestial objects, like asteroids or comets. The first planet in the system, Proxima Centauri b, was detected in 2016 by the radial velocities method. 4 years later, in 2020, it was confirmed by spectrographic studies with the help of the largest Earth-based telescope on our planet, VLT, the Very Large Telescope. According to the updates, the exoplanet lies 0.05 astronomical units away from its parent star, and it takes it roughly 11 Earth days to complete a full orbit. Estimates show that the planet's mass is 10 to 20% bigger than that of the Earth, and its radius measures about 1.3 times that of our planet. Mathematical modeling revealed that Proxima Centauri b gets about 1.5 times as little thermal energy from its star as does the Earth from the Sun. Its average temperature is 234 Kelvin, or 39 degrees Celsius below zero, which means that hypothetically there could be liquid water in some areas on the planet. As the celestial body is extremely close to its host star, however, it is likely to be tidally locked, so it faces the star with one and the same side. A dense atmosphere could compensate for sharp contrasts in temperatures, which are inevitable in such conditions, but just like any other red dwarfs, Proxima Centauri is often seen to eject stellar matter. Also, ionizing radiation flares are observed. It is assumed that such activity gradually destroys the atmosphere of the closest objects. A powerful magnetic field that could be encompassing Proxima Centauri b could offer some protection against the destructive process, but chances that there is any magnetic field there are thin. In the year 2020, another planet was confirmed to exist in the system. A space object dubbed Proxima Centauri c lies roughly 1.5 astronomical units away from the center of the system. Its orbital cycle is slightly over 5 years. As for the object's mass, it may be 6 to 8 times that of the Earth, but its radius hasn't been estimated at the time this video is posted. Depending on its size, meanwhile, the exoplanet will fall either in the category of mini-Neptunes or super-Earths. As Proxima Centauri c lies quite a big distance away from its parent star, its temperature is remarkably low, about 39 Kelvin or 234 degrees Celsius below zero. According to some observations, the planet may have a ring system whose radius is roughly 5 times that of Jupiter. Also, based on the latest data from VLT, a remarkably small exoplanet is expected to lie 0.029 astronomical units away from its parent star, whose mass is about 25% that of the Earth. If it does exist, and if this isn't another measurement error, a year on this planet lasts about 5 Earth days, and the surface temperature there could be 360 Kelvin or 87 degrees Celsius. Whether this space object is really there or not remains an open question, and additional confirmations are called for. Alpha Centauri has been listening to our radio signals for over 100 years now. But the 40 trillion kilometers of space vacuum between us are too overwhelming for us to cover at this point. It takes light over 4 years to get there, but for humans such speeds are still in the realm of fancy. Even today's swiftest state-of-the-art spacecraft would need tens of thousands of years to cover this distance. However, application of advanced technologies could theoretically greatly reduce travel time. Since the very dawn of space exploration, projects of a great number of spacecraft have been suggested that hypothetically would have been able to negotiate interstellar distances. Nevertheless, not a single one of them has been actually designed. Most of these would-be missions were forgotten, but one is still under active consideration. This is the Breakthrough Starshot program, which implies sending as many as 1,000 microprobes to Proxima Centauri as soon as in the first half of this century. They will not measure over a centimeter in size, and special thin and durable sails are planned to be created to aid the probes along. The sails will be blown out, as it were, by impulses of a highly powerful Earth-based laser. Estimates show that an interstellar probe like that is going to be leaving the solar system at a speed roughly 20% that of the speed of light, with the overall travel time around 20 years. After that, it will take another 5 years or so for the data collected by the mission to reach the Earth. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive